Let's take a look at this sample problem. Radioactive iodine 131 has an effective half-life of 7.6 days. If a dose with an activity of 400 microcuries is given to a patient today, how much radioactivity will remain after 38 days? The first thing we want to do is to determine if 38 days is a multiple of the half-life of 7.6 days. When we divide 38 days by the half-life of 7.6 days, our answer is a whole number of 5. So 5 half-lives pass in 38 days. We can work this out longhand. After the first half-life, 200 microcuries of activity are left. After the second half-life, 100 microcuries of activity are left. After the third half-life, 50 microcuries of activity are left. After the fourth half-life, 25 microcuries of activity are left. And after the fifth half-life, we have 12.5 microcuries of activity. However, how do we determine the amount left if the time elapsed is not a multiple of the half-life? This formula allows us to determine the amount left at any time. The isotope remaining is equal to the quantity of 1/2 to the nth power multiplied by the starting amount. The starting amount can be either mass or activity. And n is equal to the number of half-lives, which we obtain by dividing the time elapsed by the half-life. Your calculator can handle the math if n is not a whole number. Let's work out sample problem 2.10 from the textbook. Iron 59 has a physical half-life of 45 days. If 96 grams of this isotope is received in the lab today, how many grams of the iron will still be radioactive after 135 days pass? Go ahead and pause the video to see if you can answer this. Let's determine n, or the number of half-lives elapsed, by dividing 135 days by the half-life of 45 days. We actually end up with a whole number of 3, but let's plug it into the formula. The amount remaining is 1/2 to the n power or third power multiplied by the original amount of 96 grams. So the amount remaining is 1/8 multiplied by 96, which gives us a mass of 12 grams left after 135 days.